Data abstraction. A new method of abstraction. Here we go. So, most values are compound values, in the sense that they combine different objects together in order to create some object with multiple parts, such as a date, which has a year, a month, and a day, all combined together into one thing. Or a geographic position would have a latitude and a longitude. An abstract data type lets us manipulate compound objects as units. That's a form of abstraction. What it does is it allows us to isolate two parts of any program that uses data. We want to separate how data are represented and how data are manipulated. By doing this, we separate the concerns within our program among two different areas, and we can change one without affecting the other. So data abstraction is a methodology by which functions enforce an abstraction barrier between representation of data and the use of that data. Now, all programmers work with compound data at some point, but only great programmers embrace data abstraction in order to make their programs more modular. And you too will be a great programmer very soon. Let's take a look at an example, rational numbers, and we'll see what we mean by data abstraction. So a rational number can be expressed as a numerator divided by a denominator, where both numerator and denominators are integers, and since we can represent integers exactly, this gives us an exact representation of fractions. So a pair of integers lets us tell you exactly what a fraction we have, such as 1 divided by 3. But as soon as we actually divide 1 by 3, then we'll get back a float, which is not an exact representation, but a finite approximation of it through a binary expansion. So we want to separate the numerator and the denominator, not divide one by the other, but instead have a compound data type. So we assume that we can compose and decompose rational numbers as follows. We have a function rational, which takes n and d, a numerator and a denominator, which are integers, and returns a compound data type, a rational number x. We have another function, numer(x), which returns the numerator of a rational number x. And likewise, we have a denom x function, which returns the denominator. So we have a way of combining together a numerator and a denominator, and then we have a way of selecting those two parts. This is called a constructor. It builds a new value, which is an instance of an abstract data type. And then these are selectors, which are the functions that get back those parts of the whole rational number. What we can do then is we can start writing other functions that manipulate rational numbers, such as adding them together or multiplying them. Let's take a look. So, just to refresh your memory, if we want to multiply 3 halves and 3 fifths, we get 9 tenths. And why is that? Well, the general formula for multiplying together two rational numbers is that the numerator of the result is the product of the numerators of the first and the second, and the denominator is the product of the denominators. Adding together two rational numbers is slightly more complicated. 3 halves plus 3 fifths gives you 21 tenths. How do we get that? Well, in general, if we have two rational numbers, then we multiply the numerator of the first by the denominator of the second. Add that to the numerator of the second times the denominator of the first, and that's our new numerator, and our new denominator is the product of the denominators of the first and second rational number that we're adding together. So now we have formulas for how to multiply and add rational numbers. How do we write code that does that? Well, we'll write it in terms of our constructor and selectors. So here's a function which multiplies together two rational numbers, x and y. It returns a new rational number, the numerator of which is the product of the numerators of the inputs, and the denominator is the product of the denominators of the inputs, just like our formula says. We see that we've used the constructor to create a new rational number, and we've used the selectors to select out the parts of x and y that we need in order to complete this formula. Likewise, we can write a function that adds together two rational numbers. We give names to their numerator and denominator because we use those multiple times in our expression, and then we return a rational, which follows the formula on the right. One more function lets us really work with rational numbers, and that is equal rational, which returns true if x and y are the same number. Now, we can't just compare their parts because 1/2 is the same rational number as 2/4. So, in order to resolve whether x and y are equal, we multiply the numerator of the first by the denominator of the second, and check and see if that's equal to the numerator of the second times the denominator of the first. Tongue twister. Okay, so what you see here is that we've defined all of the ways in which we'll manipulate rational numbers in terms of three functions. And these functions implement an abstract data type for rational numbers. What that means is all of our manipulation of the numbers is written in terms of these functions. We haven't even defined these functions yet, but since we know that these are the tools we use to access the parts of rational numbers or create new rational numbers, we can write functions in terms of these and then implement them later.